at the end they're all like having dinner and there's just like fire coming and about to like kill everybody. Just like at the end of both end like that.
Oh, do they?
Like that one ends with them at the dinner table, the other one ends with them at the dinner table.
This kind of unfold.
Okay, any questions before we get started? So I thought about it, I couldn't resist kind of throwing, this is a short homework, I hope. So this is kind of to get us warmed up about thinking about these things. So the first question is, give an example of a monoid or domain, whatever floats your boat, that is not atomic. That is to say that it's not true that every non-zero non-unit can be written as a product or sum if it's a monoid of irreducibles. And style point, if you can construct one that is not a field where there are no irreducibles at all, right? So it's completely void of irreducibles, right? So it's one step to sort of find one where there's something that can't be factored into irreducibles. It's another step to say there aren't any irreducibles at all. Right. So number two, we say that an integral domain satisfies ACCP. There's entirely too many of these abbreviations, community algebra. This means the ascending chain condition on principal ideals. If any ascending chain of principal ideals like this stabilizes, more precisely, at some point in this chain, they're all equal, right? And we also say that R is Noetherian if every ideal of R is finitely generated. Some of you may have heard of Noetherian under another definition. Take this definition for the problem. That's finitely generated, that every ideal is finitely generated. So number one, so this is basically the idea is to show that lots and lots of stuff that you would ever encounter in ordinary life are atomic. Show that if R is a domain satisfying ACCP, then R is automatically atomic. Right. Actually, there was a mistake in algebra that persisted for quite a while, where it was thought that these two conditions are actually equivalent. You're going to prove if you have ACCP, then you're atomic. It was thought for a long time that if you're atomic, you had to be ACCP, that people were equivalent conditions. But this is not true. And the example that separates these properties out is so. We'll talk about that later. And finally, show that any Noetherian domain is atomic, right? So take this and see if you can bootstrap this definition of Noetherian, maybe show that that's ACCP, and then get that it's atomic. Okay, this is due like Wednesday, September 6th. Oh, and the homeworks, if you have any problem with it, I've got it up on Canvas. I need you to take a PDF of it and upload it. So if you have any problem with the technology, let me know and I will share in your lamentations, I guess. Okay. I was waiting for the sound of the thing going on, but technically it doesn't. So, okay. All right. Any questions from last time? Kevin, can you hear me? Showing up as audio on my end. Did anybody look at the recording from yesterday for chance? No? Okay. Hope I'm saying something on it. I'll check that today, but it seems to be doing audio here. Adam, let me know if you still can't hear me. I'll press on this. Okay. So we talked about these various types of ideals. I'm going to try to go through this sort of quickly here. Let me give you the following theorem. And I suspect that all of you have run across this in previous algebra classes. Let I be ideal. Number one, I is maximal. Only. Okay. Two, is prime. If and only if R mod I is. Number three, I is radical. If and only if R mod I is. And if you have, actually, this means something a little bit different from monoliths and custom domains, but if you're not quite familiar with the terminology of reduce, this means that all, let me see, there are no non-zero nilpotents. So for example, a ring like Z6 is reduced because there are no nilpotents in there, but Z9 is not because it's 3 is a nilpotent, it's not 0. 4 I know this one. I don't have a word for it, but what's the property here?
Every zero divisor is
Right. Every zero divisor. Or is no potent. Right, so these are kind of companions of each other. Anybody want to see a proof of, so I'm taking requests now. Jim's little karaoke proof thing. Anybody want to see a proof of any of this, or you guys all comfortable with this? We can move on if you like. Okay. So let's look at a corollary. I like this corollary because this characterization makes it just kind of reading these equivalent conditions make it kind of more obvious than doing it straightforward. If I is maximal, then I is prime. If I is prime, then I is radical. And so the first couple of statements are clear, right? Because the field is an integral domain, which means maximal implies prime. And any domain has no non-zero nilpotents, so prime implies radical. And if I is both radical and prime, then I is, I'll ruin a surprise, radical and primary. What happens if an ideal is both radical and primary? It has to be prime, right? Because what this means is if it's radical, then R mod I has no non-zero nilpotents, so there's no nilpotents. And if it's also primary, that means that every zero divisor must be nilpotent, which means that the only zero divisor is 0, and so it's prime. Okay, any questions?
If it's prime, it's not fourth, then we don't necessarily have it as primary, but we do have it as radical.
Right, okay, I'm sorry, run that by me one more time.
So like we have, if it's prime, then it's radical, and if it's radical and primary, then it's prime. But what we're missing is we don't have if it's prime, then it's primary.
Oh, right. So if you're prime, then you're certainly radical. And if you're prime, you're also primary. So I could have wrote this on
Okay.
this. So that's a good observation. Yeah. Okay, everybody has probably run across this as well. And I'll give you kind of something interesting that comes along with this that I sort of discovered by accident over the summer. This is what I discovered. Zorn's lemma. So this is equivalent to the axiom of choice. Let S be a partially ordered set. So I've got some set, I've got a partial ordering on it. And it's got another property, such that every chain in S has an upper bound in S. Then S has a maximum. This is exceedingly obvious, in the sense that it's very misleading because it seems like, oh, you know, this should be right. What do you have? You have a partially ordered set, and you perhaps have chains, and any chain that you happen to extract has a maximum, has an upper bound in S. Then S must have a maximal element with regard to whatever this partial order is. Now, this is, don't try to prove it, right? Because you can't. But this is very, very important. And let me give you a statement that's usually, it's probably a little bit more general than maybe one seen theorem. If 129. If R is commutative with identity, you really don't need commutative here, but I don't want to sit here and talk about left ideals, right ideals, two-sided ideals. R is commutative with one. The one is actually going to be important. And I is a proper ideal of R. Then I is contained in some maximal ideal of R. And some maximal ideal. In particular, this is a more general statement than probably what you're used to. In particular, any commutative ring with one has a maximal ideal. So the statement is this. If you have your commutative ring with one, and you start with any seed I that's a proper ideal, then there is some ideal that some maximal ideal M, such that I is contained in M, right? And from that statement right there, it follows that any commutative ring with identity has a maximal ideal, because take your seed ideal to be the zero ideal, right? And it's contained in the maximal ideal. Let me prove this using Zorn's lemma, of course. And of course, this is why people in commutative ring theory really are pro axiom of choice, because that theorem right there is absolutely central in commutative algebra. There's a paper came out in the 70s, I think, I think it's called something like 6 impossible rings or whatever. So this this person wrote this paper about, here's what we do in community frame theory if we didn't have the axiom of choice, right? And there's weirdo things that happen. So let's prove this. So let's start with our random ideal, I strictly contained in R. And what I want to do is I want to build some partially ordered set because somehow I know that I'm going to have to use this, right? So let's build this set. I'm going to call it gamma. This is the collection of all J such that J in R is a proper ideal. And I is contained in J. All right, so I just consider the set of all ideals that contain I and are proper ideals are properly contained in R. Now, let me be careful. I'll be careful in this proof here. First of all, I don't want to go along proving theorems about an empty set, right? Is gamma empty? I itself is an element of gamma, so gamma is not an empty set. And the set, I need to be partially ordered. Gamma is partially ordered by set theoretic containment. And this is probably truly a partial order because you might have two ideals, J1 and J2, that contain I, but neither one of them contain each other, right? That's certainly a possibility. But set theoretic containment is simple forms of partial order, right? It's transitive and so forth and so on, right? Okay, so to apply Zorn's limit to the set, we need every chain in F to have an upper bound in S. So apply Zorn, we need every chain in S to have an upper bound in S. And it's more or less easy to say, oh, this should be an upper bound, but you also need to show that this is an upper bound that's actually contained in the partially ordered set. So let's have the chain. Let's say J alpha. Alpha is some index set, some other crazy Greek letter. Be a chain. So what is true about all these, since it's a chain in S, each J alpha is a proper ideal, it's an ideal, and it contains I, will contain I, all right? And chain, what does that mean? If J alpha, J beta are in chain, so there are two elements, two of these random ideals, then J alpha is contained in J beta, or J beta is contained in J alpha. Right? So in general, the ideals that contain I in the set, you can't compare them, but a chain means that I've picked a totally ordered subset. Right, okay with that? Okay, somebody, let's do the usual suspects here. What's your suspect for an upper bound to this chain?
Union.
The union. So let's call it something. Let U be the union alpha in this index set of J alpha. Now notice that for all J alpha, right? I mean, this is a big fat cheat. I just took the union of all these, so certainly U is going to contain everything in that chain, right? So that makes it an upper bound, right? Well, we've got to be careful because we need the upper bound to actually be an S. Right, that's kind of the operative thing. Yeah, certainly U is going to contain everything, but I don't even know if it's in my set in the first place. I don't know that U is proper ideal. I don't know that it's good. I don't know it's a proper ideal, and I need to check all this. Right? So we need to show that U is still an element of S, and it's still a proper ideal containing I. Right? Well, let me know first. Did I miss something?
I was like, it certainly contains I.
It certainly contains I. Right, because in fact I is contained in every one of those channels, so that's no problem. The trickier part is to show it's an ideal.
You think assuming gamma, right? All this business. That's.
Yes, I do. What is S? I just
In the
Yeah,
back.
that's-
Right, S equals gamma.
yeah, that's
Yeah,
that
yeah.
blood clot running through my brain right now. That's wherever else it is. Oh, I must have used it. Yeah, I used S and that's what threw me off. Okay, yes, I'm talking specifically about gamma. Okay. Okay, number two. We need to verify that. This is the trickiest part, and this actually, I think, and it actually depends on the fact that what we're talking about here is a chain. So let's suppose. Well, to be an ideal, first and foremost, it must be a group, right? That is, so let's let A and B be U. Now, of course, U is a union of these J alphas. Right? So there exists alpha beta such that A is in J alpha, B is in J beta. Now, here's where the chain part comes in. I don't know much, but I know that one of these contains the other, right? So without loss of generality, we'll say that J alpha is contained in J beta. Right. So A and B are both in J beta. Because B is in J beta because we said so, and A is in J alpha, which is in J beta, right? Therefore, A minus B is in J beta, which is contained in U. Similarly, for all R and R, RA is in J alpha, which is in U. So this is indeed an ideal. And we need to show it. Why is it proper? One. Yes, one is a linchpin here, right? This is why one is so useful. Right? If U is not proper, then one is in U. Right? Because if U is not proper, that means U is the whole ring R, R is a ring of identity, so one has to be in U. But U is the union of all these J alphas. Therefore, one is in J alpha or some alpha. Therefore, J alpha equals R, and this is a contradiction. Therefore, U is an upper bound for the chain C in gamma. Weissorm's lemma. We are done. Because this set gamma has a maximal element, call it J, and J will contain I and be a maximal. Everybody okay with that? Now, here's a couple of things that are kind of interesting. When did you all first see this theorem, this kind of central commutative algebra theorem? Any commutative ring with identity has a maximal ideal. Did you see it in the first undergraduate class, maybe? I don't know.
I definitely saw it first semester of graduate algebra.
Okay, so you can certainly see it then,
Yeah.
right? The first time I ever saw this theorem, I was like, what is this theorem really doing? Because every ring that I could think about, it was pretty easy to pull out maximal ideal, right? Take the integer C, look at the ideal generated by 2. Take a polynomial ring over a field, look at the ideal generated by X, right? Let me give you an example to show that we've actually done something. Here's an example. This is sort of why this is important. Okay, let me give you this particular ring. So this construction is easier if I leave domain. So I'm going to let mark this. So this is just the direct product of this. This is all infinite sequences, if you will. A1, A2, AN, forever, with AI and C2. So this is the ring that's basically an infinite string of zeros and ones, right? And you add and multiply things component wise. Notice this thing's chock full of zero divisors. This isn't a domain. Can anybody find a maximal ideal of this? There's an easy way to rip one off. I can pick them off. In fact, there's a lot of them I can pick off fairly easy. Let's look at, it's the Henry gave this one. Let M1 be the set of sequences like this. Okay, so look at this ideal. Let me first claim this is an ideal. This is basically sort of the infinite vectors that begin with 0, right? Add any two things of that form, you still got a head of 0, right? And notice if you multiply anything by something like this, you've got a head of 0. This is an ideal. Everybody okay with that? Can you argue why it's maximal?
Can you do some quotient nonsense?
Yeah, that's probably the best way to do it, actually. If you look at R mod M1, this is isomorphic to C2, which is a field. And so it has to be maximal ideal. And you can also do something direct, because if you take anything, so if you take M1 and try to make it a little bit bigger, you necessarily have to add an element that has a 1 at the beginning. Agreed? And so now you've got 1 and whatever else. You also have the element 0, whatever else. So now you've got 1, 0, 0, 0 forever. So you've got the element in this new ideal 1, 0s forever. You've also got that element 0, 1s forever. Add them together, you've got the identity. So that's a maximal. Right? Okay. Now, there's nothing special about me reserving the first coordinate for this. So in general, I could do something like this, Mn, A1, A2, An minus 1, 0, An plus 1, An plus 2, with Ai in Z2. And again, R mod Mn is isomorphic to C2. It's just shifting the coordinates a little bit. So I have given you a countably infinite list of Maxwell ideals. Does everybody agree with that? Here's the $64,000 question. Is that it? Or are there any others? Hush silence permeates. There are a lot of others, but they're hard to find. Let me give you the C. Let me rephrase it. Let me give you a C. Consider the following ideal. Consider the direct sum. Now remember what the direct sum is. Well, actually, we can kind of characterize it simply for this case. The direct sum is everything in here, the original ring, that ends in an infinite string of zeros. Right? That's it. Notice when I think about it that way, it's easy to see that this is an ideal, because if you take any two elements that end in an infinite string of zeros and add them up, you have to end in an infinite string of zeros, right? And if you multiply something that ends in an infinite string of zeros by something else in the ring, it ends in an infinite string of zeros. Everybody on board so far? Now, by our theorem, I is contained in, well, some Maxwell ideal. But it's easy to see it can't be any of these, right? It can't be contained in this Maxwell ideal because, for example, the element 1, 0, 0, 0 forever is in this ideal, not in here. And in fact, more generally, the element 0, 0, 0 and 1 in the nth place and 0 is everywhere else is in that ideal, but not here. So this ideal is not contained in any of the Maxwell that I've listed. So somebody write me a nice characterization for what that Maxwell ideal looks like. Do it, and you know what? I'll give you an A in the course, and I'll pay for your TDs every day for this semester. If you can write down the Maxwell ideal. It's actually contained in uncountably many, and you're never going to be able to write it down. And this is where choice comes up, right? It's fairly easy also to see that this thing right here isn't a Maxwell ideal itself. So to build your Maxwell ideal, so I want to get out of your stupid course, right? So I want to try to build this thing. You're going to have to put in something that doesn't end in an infinite string of zeros, right? So maybe you throw in this element. 1, 0, 1, 0, 1, 0, alternating like this. Glue this to this and make a slightly bigger ideal, right? It's fairly easy to see that when you adjoin this to this, there's no way you're going to get the identity, right? Because there would have had to have been 0, 1, 0, 1, 0, 1 in this, right? So you make this choice and you make the ideal slightly bigger. It's still not maximal. So now you've got to make another choice and add something to this. But now you can't do this. Because if you add this and then this, then you've got the identity. So you've got to make some other choice, and it gets worse and worse. Right? So this really, I like this example because it really shows that something's happening and the axiom of choice here. You're not gonna be able to write down the form. You can write down some of the Maxwell ideals, they're nice, but the one containing this one, good luck. I mean, if you could do it, it would be totally worth it to me for you to get out of this course, because I'd love to see that, but you're not gonna do it, right? So because you have to make so many choices, in fact, many choices, you just can't write it down. Okay, any questions on that? Okay, so let me give you this is kind of what I promised about the theorem that I sort of ran across this thing. I gave a talk in Austria, and it was, let's say it was 75% kind of expository about stuff that's going on. I ran across the following theorem, and I'm really ripping off the author because I can't remember his name without the slides. Give him a shout out next time. This was around 1976, I think. So here are two theorems that you all have probably seen. And you're going to see this again later in my, but how many of you seen this theorem? Any principal ideal domain is a unique factorization domain. You saw that probably at the beginning out. That's right. By the way, how many of you have seen the proof that Euclidean implies PID? Seen that at some point? Actually, that proof is actually easy. Euclidean implies PID. This one is a little bit complicated. Two, every PID has a maximal ID. Now, this may look stupid. Why are you writing this down, Jim? Because you already know that any commutative ring with identity has a maximal ideal. But the point of me writing down this, neither can be proven without choice. Neither of these theorems, you cannot even prove that a principal ideal domain has a maximal ideal without the axiom of choice. I should probably phrase that a little bit better. You can't prove it in ZF axioms. You need ZF and something else. And in our case, it would be choice. But principal ideal domain, this is why that proof is more complicated. You cannot do this without using the axiom of choice. And you cannot do this. I mean, forget commutative ring of identity. You can't even prove PID has a maximal ideal without using the axiom of choice, which I find kind of interesting. Okay, any questions on that?
If I may backtrack to one thing, and we may not be able to answer this in the context of this class, but I was just thinking, you need choice for something like this. And so in that previous example, we took this uncountable, or this product of Z mod 2Zs, which is, kind of an odd ring in some ways. And our proof, which we've seen probably at some point, we just kind of casually said, oh, let's take the set of ideals containing I, and this is a partially ordered set. And I never really understood why this was in fact a set always, because like the ring could be very, gnarly. And so I don't know if this is worth getting into, but it's something I've never actually understood.
Right. Well, the ring itself is a set. It's assumed to be a set.
Right, yeah.
Right. And so what you're looking at a collection of subsets of that ring.
Oh, right, yeah. So then that's always
right.
Yeah.
But this actually does run into, so you've heard of the surreal numbers. Right? They're like, these the notion of infinite Tesla. It's a mess. It's a fun mess. But there is a field of surreal numbers, and I've used this at one point in a paper to do something crazy. Actually, it was the idea of a former graduate student of mine, but the surreal numbers is technically, so what he's worried about, the set of surreal numbers is actually not a field because it's too big, right? It's too big to be a set. So it basically functions like a field, but there's so many elements that it's not really technically a set. And there's some subtleties in there I'd have to read about. I got it too deeply in that, but technically people treat it like a field, but really there's technical problems with its size in a certain sense. So, okay, so I'm actually going to talk about some stuff that has to do a little bit with factorization here. Some of this, might be, well, I'm sure that you've seen, these definitions before, but maybe we'll look at them a little bit deeper. Irreducibles and prime. So, let R be an integral domain. One. And let's let X be an R. Say a unit. If X divides 1, that is to say, there exists Y and R such that XY equals 1. Any commutative ring with identity has one unit at least, and that's namely 1 itself. B or 2, irreducible. If X equals AB implies A or B is a unit. So what it needs to be irreducible is whenever you try to factor it, it's irreducible if one of the factors is forced to be a unit. And finally, prime, if X divides AB, implies X divides A or now, maybe in a basic number theory course, right, like an undergraduate course, you might have seen either 2 or 3 for the definition of prime. Right? How many of you have seen this definition here for prime? It means to be prime, it's only factors or units, right? These two are actually different in general. But if you're living in a UFD, like for example, the ordinary integers or somewhere you might start off, a number theory, these two are equivalent as long as X is not 0. Irreducible and prime are the same concept, not 0. However, it bifurcates if you're not in the UFD. And I remember, I don't know, what is it? I remember, of course, went to grade school in Tennessee, and I remember back in the day, shortly after learning multiplication tables, they told us the fundamental theorem of arithmetic. I mean, they didn't put it that way, but they were like, every element can be factored into primes, and maybe the word uniquely was, in fact, yeah, the word uniquely was thrown about. And I remember starting in 3rd grade, asking the teacher, is 1 a prime or not? And apparently the theorem in Tennessee is in odd numbered years, 1 is a prime, and in even numbered 1 is not a prime. But anyway, when I got to about 5th grade or something, I figured out that 1 could not be a prime. Can anybody tell me? So this would be something that if you use the definition of prime that you usually get in a beginning course, like in high school or grade school, when you say, oh, prime numbers are numbers whose only factors are themselves and 1, right? A natural question would be, is 1 a prime? Right? Can anybody tell me why it can't possibly be? Let's assume that you believe the fundamental theorem of arithmetic.
It's because it's 1 squared and 1 cubed and 1 fourth and 1 fifth.
That's right. That's right. If you're going to believe in unique factorization, it's completely out the window if you're going to allow 1 to be a prime, right? Because you've got it's bad, right? So this is why we have this notion of unit, because when it comes to factorization, it doesn't really bring anything new to the proceedings, right? Can anybody So let me, actually, let me give you a proposition here. Let me, sort of couch this in terms of ideals as best I can. Proposition, 1 through 2. Let R be an integral domain in X and R. A. X is a unit in R. Oftentimes, if you can count something in terms of ideals, it can be useful. That is correct. It means that principal ideal generated by X has to generate the whole range because of the fact it's a unit, you've got one in that ideal, and now you've got everything. B, X prime, if and only if it's prime ideal. What a shocking twist of events that is. C. How about that one? This one's a little bit less common, so to speak.
See, maybe Maxwell, but I was like, wait, is that? I might be thinking of something different, like if R is more specified.
It is a maximality condition.
Maximum
Right. If and only if the ideal generated by X is maximal among the set of principal ideals.
So in a PID, it would be.
That is correct. So in a PID, that's a good observation. A PID will be truly maximal. But what I mean by maximal set of principal ideals is there certainly are ideals that may contain it, but every ideal that properly contains it cannot be principal. It requires more than one generator. So let's look at this really quick. Let me kind of follow up on what I was saying here. Let R be a domain. Get marked by free roll. Let R be a domain, and X a non-zero element.
That's a question, no.
Mhm.
I have a question.
Sure.
If we're gonna say that X is maximal among the set of principal ideals. How does that work in Z, for example? Because,
Then it will be
Set-
maximal in the set of all ideals.
well, the set of all ideals of Z would include Z itself, would it not?
No, okay, yeah, you're right. I should be careful about this. When my definition of maximum prime, I hope I did this, I thought I did, is they have to actually be proper ideals. Right, so when I talk about a maximal ideal, if I talk about a prime ideal, they always have to be proper. So let me add.
So when you define maximum of a ring, that makes sense.
Is that better? Maximum on the set of proper principal ideals.
Okay.
Right, because in any ring with identity, technically speaking, the ideal generated by one is an ideal. It's not proper, and it'll contain every other ideal. Okay, so and X be prime, then X is irreducible. So if you have any non-zero prime element, then it has to be irreducible. Notice non-zero is important. Zero in an integral domain is prime because zero is a prime ideal in an integral domain. However, zero is not irreducible because zero is zero times, zero. And neither zero nor zero is a unit. Alright, let me see if I can. Quick proof of this, suppose x equals AB. Right, and we're assuming that x is prime. Without loss of generality, x divides a. Right, because x divides this product, the quotient is 1, so it has to divide one of them. Without loss of generality, we'll say that x divides a, so a equals a prime x. So x equals AB, which is a prime x b. And so what I get, if I take this over and factor out the x, zero. Now, R is an integral domain, which means this product is zero. So either this is zero, which it is not, or this is zero. Therefore, A prime B equals 1, and B is a unit. And there you go. By the way, am I without loss of generality? If I had said X divides B, then A would be the unit. So there's the symmetry there. Okay, any questions on that?
I guess just a quick sanity check. So let's say we're in the context where R is a field, and I guess 0 would be maximal among proper principal ideals, but 0 is still not irreducible.
You know, let's see.
Unless I'm just not quite saying.
Yeah, no, you're absolutely right. Here, let me cheat again. Not a field. Right. No, that's actually the only pathological case where that can happen, but he's absolutely right. If it's a field, 0 is certainly a maximal proper ideal, but it's maximal, but it's not irreducible. Right. Thank you for that. Yes,
I'm gonna complain one more time. What about 1? Are you claiming that in Z, for example, are you claiming that 1 is irreducible?
no, it's a unit.
So then in our definition of irreducible, we probably need to say it's a non-unit then.
I meant to say that, yeah, that's right. I meant to say that. Any of these definitions, let's see, let me make sure that I wrote that
Because
down.
technically, we have x equals AB implies A or B as a unit, which would still hold for 1, so I think we need to clarify. Or
No,
irreducible.
you're absolutely
prime
right.
is
I'll update that, yeah. So when you talk about irreducible primes, you want them to be non-units for sure, yeah. Okay, y'all are on top of this, kid. Any questions? All right, well, I will see you all on Monday. All right.
It is. Yeah, figure that way, there's no way out. Like unusual.
I would honestly never look at it early. If this wasn't factorization theory, my opinions would be.
Yeah.
Something.
Oh, yeah. Totally understand.
That's all the ways.
But, yeah, at this point. With I hope that's.
Not being able to. If it's exciting being awake, because they're like figuring something out, then that's. But if it's like,